Today we're going to look at infrared spectroscopy. And to begin with, we need to consider what happens when molecules interact with infrared radiation. So I thought we'd start off by just recapping the electromagnetic spectrum a little bit and reminding ourselves about how the electromagnetic spectrum goes from really long wavelength radio waves through microwaves, infrared, visible, ultraviolet, X-ray and gamma rays, and that the wavelength gets progressively shorter. Our frequency, as the wavelength gets shorter, our frequency gets much higher. Because our waves are squished closer together, and you have to remember that as frequency is higher, then our energy. So energy also increases as our wavelengths get shorter and the frequency gets higher, because E is equal to hV, with V being frequency. So energy is directly proportional to frequency, but it's indirectly proportional to wavelength. So a long wavelength means a low frequency, which means a low energy, whereas a short wavelength means a high frequency and a high energy. So what does this mean for molecules? So you can see on my diagram we've got a little bit of an idea of what the size of the waves actually are in comparison to real things. But what does this have to do with molecules? So if we consider a water molecule, just move this out of the way a little bit. So we've got our water molecule. Now, if water molecule gets targeted by or interacts with infrared radiation that's fairly low energy, something like microwaves, then our water molecule will actually start to rotate. And that's how microwaves in fact even work. So that's how microwaves work, by making water molecules rotate. So they specifically emit the correct frequency that makes water rotate. They don't interact with other molecules. That's why microwaves are particularly poor at cooking food that doesn't have a very high water content, and because they only really interact with the water molecules that are in the food. Now, if we increase the energy of our infrared radiation a little bit and move into the infrared region of the spectrum, rather than rotating the molecule, what happens is the molecule, it starts to vibrate. So our molecule will vibrate while it is undergoing infrared radiation. And the whole molecule will vibrate as it's gaining kinetic energy. But equally, the actual bonds within the molecule will stretch and bend. So that it's difficult to show on the screen, but the molecules within will bend and stretch. And this is what happens when infrared radiation is absorbed. Now, if we increase the energy further and move into visible light, then we just start to look at electronic energy levels. And our electrons are able to jump between energy levels. So we might have an electron jumping. So if we just fill in some electrons, if we put the right amount of visible light in there, we might get promotion of electrons, and they might jump from, say, a 2p up to a 3p. So visible light causes electrons to jump. If we move into UV, then we can start to see, as we've seen when we've been doing photodissociation and free radical reactions, you actually start to get breaking of bonds and homolytic fission once you get into the high energy of UV light. Now, all of these different interactions with different types of electromagnetic radiation are useful for different types of spectroscopy, but the one we're really focused on today is infrared. So I want you to really focus on this idea that if you irradiate molecules with infrared, they get warmer, but that happens because the molecules vibrate, the bonds stretch, the bonds bend, And different bonds stretch and bend at different specific frequencies, and because they kind of resonate at the particular frequency that affects that particular bond. So we're going to move on now and have a look at the bit that you're likely to get examined on, which is actually looking at the infrared spectra and being able to interpret them. Let's start by looking at the axes that our infrared spectrum comes on. So some points to note that along the bottom we have wave number, which is a bit of a made up thing. The physicists will get angry at me again because it's not an SI unit. Wave number is how many waves fit into a centimetre. Okay, so a high wave number, 4,000 is the highest wave number we've got on here. That means we've got 4,000 waves fitting in a centimetre, so this must be a short wavelength. So we're looking at, this is going to be short wavelength, which means it's high frequency and high energy. Okay, whereas at the other end, down at about 500, we're looking at only 500 waves per centimetre. Therefore, we're looking at a longer wavelength and a lower frequency and a lower energy. Now, the way the spectrometer works is the infrared radiation is passed through the sample, and the sample absorbs some of it, anything that's the correct frequency, and then the infrared gets picked up by the detector at the other side. So if you didn't put a sample in the machine, or if the machine had a sample that didn't absorb any infrared radiation, then you would have 100% transmittance all the way across at all the different frequencies. So a line along the top at 100% means you haven't got anything absorbing and removing it. So 100% of the infrared that's being passed through is going all the way through and being picked up by the receiver. Now, if we consider what happens when it actually comes into contact with a molecule, so if we consider the water molecule that we looked at, what we'd get, it's only got OH bonds in it, so it's only got one type of bond to absorb energy. You would get 100% transmittance all the way across until we get to whereabouts it would absorb, and then you'd get a trough. So this trough, around 3,300, 3,500, this is a broad trough. We call it a peak, it is a trough. And it's where we can see that we no longer have 100% transmittance. There's a molecule with the bonds that are absorbing energy of that particular frequency, at that wave number. Now, as I mentioned before, the first thing that happens in infrared radiation is the whole molecule vibrates. And this tends to happen at a fairly low energy. So in the region around 1,500 to about 400, so up here, you would get a whole array of peaks and troughs. And we call this area the fingerprint region. So this is low energy, and this is due to the whole molecule vibrating. Now, it's called a fingerprint region because every single molecule can be identified by this fingerprint region. So if you've got a database of all the different molecules that exist, you can look them up, and if you've got a pure sample, you will be able to tell from the fingerprint region definitively that it is that exact molecule. Now, you're not expected to have an encyclopedic knowledge of different molecules for your exam, so you're not expected to be able to identify things from the fingerprint region, but you do need to be aware that that's what it is. You need to be able to look for particular troughs or peaks later on in the higher energy section that show particular chemical bonds, because those particular chemical bonds, like an OH bond or a CO bond or a C double O bond, a C double bond O, would give you an indication of what functional groups you've got in your organic molecule. Now the exam board are really nice. They don't expect you to remember exactly where all these are, and in the data sheet they give you with your exam, they give you a list of the different bonds and what wave numbers you can expect to see them as. So you can see, I already showed you that an OH in an alcohol or in water you'd expect to appear around 3,200, 3,500. If you had something with an aldehyde or a ketone, so it had a carbonyl carbon, I'd expect to see a really sharp peak around 1,700. Okay, these will make more sense when we look at other things. So if I had a sharp peak around 1,700, and I also had a broad peak over here, my drawing is nowhere near as good as an actual spectrum, then you'd see, oh, I've got a broad peak around 3,200, 3,000. So that must be an OH, or it could be, and I've also got a carbonyl group. So I've got a C double bond O, I've got a peak around 1,700. So I can see that I must, if I've got both of those things, it's quite likely I've got something like a carboxylic acid. If we get rid of this peak and put it back in, so CH appears around here, so we might get some peaks around here. Then we go, oh, all I've got is some peaks just before 3,000, so that would be my CHs, it's a sharp peak. And I've got a peak around 1,700, so I must have a carbonyl, so I've either got an aldehyde or a ketone. I definitely haven't got the broad OH peak, so it's not a carboxylic acid. If I just had the broad OH peak and I didn't have the 1,700, then I'd know I was looking at an alcohol. Okay, let's have a look in the next few slides at some spectra, and you guys can have a practice at doing this. So let's have a look at this spectrum where we've got, and we're told it's potentially either ethanol or ethane or ethanoic acid. So we need to look at the spectrum and look for our characteristic signs of what kind of bonds it's got. So we can see we've got our broad peak here, which we know is going to be due to an OH bond, and we've got this peak here, which you'll see in pretty much every single organic molecule. This is a CH stretch, and noticeably we haven't really got anything around 1,700, so we can say that it's got an OH, it's got CHs, so it must be ethanol. So let's consider this second example. So we've been told that this is either butanol, so another alcohol, or it could be butane, so an alkane, or it could be butanal, which is an aldehyde. Okay, so we're either looking at an alcohol, an alkane, or an aldehyde. So if we look at the spectrum, it's a pretty bland spectrum. There's not a right lot going on in there. We can see we definitely don't have anything around, there's no broad peak around 3,000, and there's nothing happening around 1,700. The only thing I've got in there is this sharp peak just before 3,000, which is due to my CH bond. And if that's all that's in there, then we know that we're looking at butane. So this is the final spectrum we're going to look at in the video. We're told it's a choice between propanol, so an alcohol again, propanone, a ketone, or methylpropane, which is an alkane. So if we have a look at the spectrum, we can see our fingerprint region. we can see we've got this sharp peak, sort of about 1750. And we've got a peak around 2800-ish. And we don't have anything where we might expect to see an alcohol. So there's no OH group. So we know it can't be the alcohol. We know it's got a CH stretch. So it could be the methyl propane, but importantly, it's got this stretch around 1750-ish, which we know is due to a C double bond O, a carbonyl stretch, which means we must be looking at, I'm sure you've all got it, must be looking at the propanone. Okay, that's all from me for today.